We should make K a co-host. No, that's not what I wanted. Okay, Theo's got it's great. So let me just make K a co-host really quick here. There he is. Co-host. Okay. And Theo, you are sharing, which is great. Let's see, where are you? Theo, can you unmute yourself to check that we can hear you, please?
Yes, can you hear me now?
I can.
Okay.
Let me try to figure out how to, are you going to have your video on? Are we projecting?
Yeah, sure. If you want, I can turn it on.
Yep. Okay, that'd be great. Just for partially because of the recording purposes.
Second. Okay.
Okay, I think if I pin you, it makes most sense. Theo. Oh no, that didn't work quite like I was hoping, I guess. Oops. I am just not winning today, I think. Move pins. Okay. Theo, is your video on? I can't yet see you. You're also.
Yeah, can you see now?
Can see you now. Okay, so you should be good to share, I think.
Let me share this screen.
Okay, that's great. All right.
Okay. All right. Can you guys all see it?
Yeah, it's looking good. Okay, folks, I think we're ready. Sorry for the delay. I confused Theo because I, for some reason, still haven't learned to specify how time zones work in this, you'd think by now. So Theo, computational scientist at Caltech, he builds and maintains a ton of the database infrastructure, the machine learning toolkits, a lot of the front-end interfaces that are all used within the collaboration. And so I'm super happy that he was willing to put together some slides as well as the notebook for today about some of the ways in which we do alert classification within ZTF. And so my understanding is he'll talk through the slides and then show off the notebook, what it's about and so on. And then so thanks for being here, Theo. Really appreciate it.
Yeah, thank you for the invite. Yeah, so the idea would be to kind of give a quick overview, not too much in technical details, of what kind of machine learning we do for ZTF, and more specifically for real-time inference for the alerts. So I'm sure that some of it you've already heard about it. But in general, why do we need machine learning for astronomy is that we're just getting larger and larger data volumes, right? So on average, it's doubling or so every 2 years. And for the case of ZTF, we cover half of the northern sky every night, which is on a, let's say, bad day with not that many alerts, 300,000 and sometimes over 600,000. And even if we had more and more people that just wouldn't do it, right? So, and we're also constrained by anyway how many of those alerts we could actually follow up. So we need to make choices rather quickly and based on many parameters. And sometimes there's just too much for a person to look at. And also, even if we got many people to just work on this, different people make different decisions and they have different interests. So the goal would be to kind of streamline this process, right? Make it automatic enough that we can provide metrics that are easier to look at than the entire alert packet plus images. And also that people can filter on automatically and then get only what they're interested in. And so as I said, the goal is kind of to mimic the human thought process, or at least get close to it and make it a little faster. And so for now, the goal of machine learning in ZTF isn't really to make the decisions. That might be the path forward in the future. There are folks that are working on models that would do just that, but the goal would be rather to improve human performance and also throughput, just to give you only the alerts that you're interested in. And also it can run in real time compared to a person, right? So it makes it much more flexible because you can just have it run during the night in real time and then worry about it in the morning. So the goal would be to annotate the alerts, right? Add more information, but actually having more information means having to look at less of it because the information that you provide is more useful than all of the scores individually. And so, yeah, the ultimate goal is to filter out all of the stuff that you don't want to look at as an individual, and for different people, that's going to be different things. So we want to provide metrics that then they can apply filter-ons, right? So the scanning process works as such. We get all of those alerts every night. Then it goes through a broker, Kowalski. Kowalski gets all of the alerts and takes care of running all of the machine learning and then applying the user-defined filters and posts it to our web platform, our Marshall Fritz, where people can just scan for all of the alerts that they got during the night. And so as you can see, that kind of sums up the goal here, is that we'll have the machine learning run in Kowalski on the raw alert packets. Then we filter out what we don't want to look at. And then when you're in the broker, you go from those plus 300,000 to something like 200, or if you have tighter constraints on your filters, could be way less than that. So we'll have an example later, but for the Bright Transient survey that I think Dan already talked about, my understanding is that you go from these 300K alerts to something like 30, which is much more manageable. So what kind of data do we have access to? So we have data from ZTF itself, so catalogs of objects that throughout the lifetime of the survey were classified. But also data from other surveys or groups of people that we can cross-match with our alerts. And so we have the real-time data from the alerts, but also we have bi-monthly data releases with much more complete life curves that people also work with. But mostly we have unlabeled data. And most of that data, right? So the alerts and the bi-monthly data releases, they have certain amount of metrics, but they're not characterized. You don't have a classification for it. So we'll look at some examples of the models that we run every night, just to give you an idea of what is doable, what we've done so far, and also kind of inspire you to maybe get some ideas based on whatever is your interest of what you could achieve with machine learning. The first example is SAI, which is the alert classifying AI from Dima Duov, who was working here before me, and he developed five binary classifiers, right, that are independent from each other, and they're running only on the alert data. They're not relying on anything else. And it's a model and architecture that is easily adaptable to many science cases, simply because it's using most of the data we have in the alert packets. It's using everything that's available. So it just depends on whatever data set you give it, right, and whatever labels you have to train your model, but you shouldn't have to change the architecture drastically to get some good results. So the 5 models that are running are to classify if an object is orphan, hosted, nuclear, variable, or bogus. And it uses both the numerical features, but also the cutouts, so the images. I'm seeing that someone raised their hand. I don't know if there's a question. No.
Yes, so I have a very quick question. How do you select these models? Like there can be like a lot of models, right? Like for doing the classification. So how you selected only these 5 models? Is there any criteria or something?
No, I think it's rather that it's simply that those were specifically developed a few years back to classify the ZTF alerts.
Oh, okay. Thank you.
So yeah, it uses the numerical features, but also the cutouts, the images. And the architecture is simple enough that you can run inference really fast in real time on all of the alerts as they come in during the night. And this provides some of the metrics that scanners will then filter on. So what's the data set made of? So this is a great example of what kind of data you can come up with for these models. So it's 200 individual alerts. So that can mean multiple alerts for the same objects. And they've been labeled by hand using an active learning approach, right? So some of the data set was labeled, then the model was trained, and then you get some of the results, and you look at what has a high confidence, low confidence, and close to the decision boundary, and you just relabel it by hand, which helps kind of go through labeling all of the data set quicker. So the data set has a certain number of known variables, nuclear, transient, hosted, orphan events, and bogus alerts. So this is what the architecture looks like. So I'm gonna break it down into different sections. It really reflects what I talked about before, is that you have one part of it that is just dedicated to the numerical features, and then a second part of the model that is dedicated to the images. And then the two of them are concatenated. They go through one or two dense layers, and then you get a score out of it. And one tool that we're using heavily for machine learning is weights and biases, which you'll have a chance to kind of play with in the notebook if you don't know it already, which is a great visualization tool, and not just visualization, but tracking and doing versioning of your models. And especially with their sweep feature, which is kind of a fancier grid search that helps you figure out what are the best hyperparameters for your model. And so what are the advantages of having 5 models instead of just one that has 5 classes? Is that the idea behind it is that if you have independent classifiers, it's easier to just add some more labels for one of the data classes and retrain the model if you're not happy with the performances and the results that you have in production. And also an alert can be classified as multiple things, right? So you could have, I guess, an orphan that is also a variable, and that approach kind of makes it easier to, and I mean, in general, allows to have anomaly detection, right? So if you have an object that is both orphan and hosted, that doesn't really make any sense. So you're gonna have to, that allows you to identify those edge cases that then you can look at and probably reclassify, add to your data set, and rerun your training. And yeah, and also the idea is that people can create custom filters based on multiple of those scores. So it doesn't have to just be, okay, give me the alert if it passes that score, but it can be rather, give me the alert if it passes that score, or that score plus that score combined is superior to that value. Another example, and this one has a nice kind of overview of what the architecture looks like, is BRI, which is a real bogus classifier, which now is even running not just in Kowalski, but directly upstream on the raw alert packets. It's the DRB score that you might see when you work with the alerts. And this one doesn't even need the numerical features. It's going to look only at the images to kind of identify, well, is there really something to look at, or is just, just an issue with this abstraction, some noise. And this is the kind of model that are, let's say, even more essential than ASI, in the way that this is going to just tell you whether or not what you're looking at is bogus. And then another example, which is the one that we'll go through in the notebook. This is way more recent. This is from this year. This is a model from Nabil for BTS. And the goal is just to kind of help the scanners with early detection of bright transients. And the idea is to, I mean, Dan talks about it, but it's to kind of identify bright transients to start the follow-up process earlier than it was possible before. And in the future, I think that Nabil mentioned that they want to even trigger follow-up automatically based on the score that they get out of these models. So that gives you an idea of, when you develop confidence in your model, right? If you get great results, it's totally reasonable to even use it in the decision-making of whether you follow up something or not, even without having to go through the scanning. And yeah, so this is what I talked about before. We use Kowalski to run all of these models. So they simply run sequentially on each of the alerts. And then you end up being able to filter and provide those scores. And to give an idea of how Kowalski works, so how do we process those large amount of alerts nightly and still be able to run inference on all of them? it relies on the MongoDB database. So it's just JSON documents, which is very nice because it makes it human readable and it's easy to write filters. And what we do is that we just rely on Dask, which is a way to parallelize and scale how many alerts you can process at once. So each of those workers can be assigned one alert at once, and otherwise stuff that is waiting is just queued. And each of them are able to run the 5 models that I mentioned. And the idea behind this, and this is kind of to encourage you to explore machine learning and to realize that it's not just because you have a great model and it doesn't stop here. It's pretty easy to actually get it to production. We have kind of a drag and drop model deployment system where we just specify in the config, like the model name, what inputs it has, the order of the features, thing like that. And it's able to just download it to like pull the model and just run it on run inference on whatever instrument you trained it for. So this is a quick example for the BTS model, right? So Nabil just gave me the URL to his model, the list of numerical features, if he wants to use the cutouts or not, in which order and what's the format. And then the config, it just very simply looks like this, right? We have a key for each instrument. So one of them being, of course, ZTF. And then we have the list of the models with whatever we need to get them up and running. And then folks, as I mentioned, can grab some scores. So let's say here, as you can see on the left, they say, okay, so this is a match key. This is your conditions. So you'll say, okay, I want only the alerts that have a BTS score greater than the array, than 0.8. And then from those alerts, I want to grab the acai score, and then I want to add an annotation on my object once it's posted to our Marshal with that score. So this is also a way to kind of, because you don't want just to have it as a black box where stuff goes through and then you get your alerts and you have no idea what happened. And this is a way to retrieve the scores as well. Okay, so this was the kind of like quick overview of what we're able to do, what kind of data we have that is available, and what kind of models we already have running in production. So I guess now, Michael, we can probably look at the notebook.
Yes, are you in a position to share the notebook and walk through what the students will do?
Yeah, how do you want me to do this? Just kind of go through.
Yeah, I think it's helpful to sort of open the notebook, sort of talk through kind of what's in there and in the end what they're going to work on, and then we can break off into having students work on the stuff.
Yeah, okay, sounds good. Okay, let me see if I can zoom a bit. Great. Is it big enough to be readable, or do you guys need me to zoom a little more?
Just let us flip off the front lights for a second. Yeah, the black background is struggling here. Yeah. Yeah, maybe the curtains. I wonder.
I can try to turn it to black background.
And we'll shut up. Yeah, I think that combination will be enough. Kind of weird, but it's fine. All right.
That hurt.
All right, there you go.
Okay. Yeah, so this is the notebook that I prepared. You guys can take your time to kind of read through it after I just gave a brief overview. But so as I said during the quick presentation, we're gonna have, this is an example of how we kind of facilitate the scanning process, right, for the Bright Transient survey by teaching neural networks how to look at the cutouts and the metadata from the alerts, just like a human would. So this will give you a better understanding of the model's architecture and the process of how we train it, evaluate it, and how we fine-tune it. The only thing we won't really mention here is how did we create the data set. But briefly, we have a list of objects that the Bright Transient survey has classified, and we can simply go back to the broker that I mentioned before, Kowalski, and just pull down the entire list of alerts for the objects that you're interested in. both the images and the features, and then create a data set that you can run inference on. So I had a quick reminder for CNNs. I don't know how familiar you guys are with it. Probably you are, but yeah. So the idea would be essentially to look at the cutouts, and this is the way that we want to do it. And this is composed. It's a very simple convolutional block kind of model where you have just two blocks, right? With a max pooling layer in between, and this allows you to kind of extract enough of the features from the images to classify. And important to mention that, so in this very example, we use both the numerical features and the images, but you could totally just try to create models that just use one or the other. Though if you did, you might have to have a bigger architecture for those two individual parts. So the input for the images is, so we have the science image. That's the image that was taken overnight. We have the reference image, and we have the subtraction of the two that just shows you the point source that you want to look at. And for the metadata, it's just perceptron, like you know already. And it's just all of the metadata that IPAC gives us, which is a ton of numerical scores. I think there's something probably over 30 of them, if not more. And then we end up concatenating the results of the two of them into one dense flattened layer, which goes through one more layer, and then at the end, we're going to get a sigmoid function to get a score out of it, from 0 to 1, 1 being this is the right class, and 0 being this is not the right class. So why do we need AI for all of this? I prepared this before I prepared the presentation, so there, a lot of it you already heard about it, but this summarizes some of the things that I talked about. So you can use this kind of as a way to get whatever answers you need based off the presentation. But yeah, in the case of BTS, so this is something that Nabil gave me. The mission is to kind of classify automatically objects that could be submitted for follow-up, so then they can be classified with spectra. And it's all of the bright extragalactic transients. And so he's using the BTS model running in Kowalski, and then I think he has some kind of other software to grab the results from the alerts, and then potentially trigger follow-up. So first, you'll see, so we'll define some configs a few times in the notebook. First, we'll define configs like within the notebook, which are those that we'll use when we're running the model from the notebook. But then we'll define config on weights and biases. So this is a time for you guys to probably create an account. Did they do any AI stuff already this week? I don't know if they had a chance.
This is our first foray. Yep. Okay.
So you probably want to go to weights and biases and create an account soon, because this is going to come up very soon in the notebook. It's free, you don't have to do anything. You can just create the account. So yeah, so we'll define the different, like the model here first in different like notebook cells, but then we'll define a proper cleaner method to look at it. So those are the two convolutional blocks that we have, right? So with two convolutional layers, max pooling and dropout. And one of the things that you play with later in the notebook is playing with the different hyperparameters, like the dropout values, to see how that influences the performances of your model. And then we have the metadata block, which is extremely simple. It's just go through two layers. It's as simple as it gets. And but that's a nice thing about being able to concatenate images and numerical features, is that you don't need an intricate model for each of them. Because some of what you have in numerical features and the images is somewhat related. And so by concatenating the two of them, you can get some nice results. There's depending on your data, you might even be able to concatenate first and then have whatever layers you have in your model. But this proved to work well for our science case. So then we concatenate everything. We have a dense layer, a dropout, then a less dense layer with a score. So this is what it looks like, right? the convolutional layer that block that is a bit fancier than the metadata one. And then you end up with simply one neuron with the score. So you'll have some cells here and there to kind of just try if the code works before actually, pulling the data set. Yeah, I didn't mention that, but that's something that you could do now if Mike already shared the notebook, which is you can just uncomment those 2 lines, right? Then run it, because the data set is not that big, but it's it's a few gigabytes. So make sure you have enough space for it.
And I'll just confirm it should be up in the day 3 GitHub.
Okay, awesome. Right, so we'll have a nicer kind of class to which we can pass the config, and it just creates the model for you, which is make it a little easier for this session. So great. Okay, we have a model, right? But we have no idea if it's able to actually, it's not, we don't have an idea. It is not able to classify anything. At most, it's going to give you something like 0.5 of accuracy, because it just gets stuff at random, has one chance out of 2 to classify it well. Might be higher than this, but yeah, you need to run it for sure. You need to train it. And so for the training loop, we have way more parameters that we need. But essentially, of course, when you need to look at, for those that already did some machine learning before, is the batch size, the epochs, the learning rate, what kind of loss function you're using, what kind of optimizer you're using, and ideally set a seed so that when you run your models multiple times, you'll get the exact same results, because it starts with the same parameters. And then we have some other parameters that are used for some of the mechanisms that we have in place to stop the learning process earlier than just whatever number of epochs you pass, if it's just not learning anymore. And we have also a list of what numerical features the BTS model is using, because compared to SI, Nabil kind of played with the different features and figured that this is what was enough to get good results, and not just enough, but this is what gave him the best results, is to constrain to using only those features, and including 2 of those that are not in the alert packets, but those are computed from earlier alerts for the same objects, right? So that's also something that you might consider for your models, is to kind of introduce some numerical features that reflect the evolution of one object, like its age and its peak magnitude so far. In the alert packets, you have the history of previous candidates, but up to 30 days. So if you have, let's say, especially, I guess, a variable, something that lasts for a long time, you might want to have access to a database like Kowalski to pull more information from previous alerts. So then we'll just load the data, split it in the training and the validation sets. And then we have a data generator, which it's clearly not essential for this. The reason why I still added it here is that it's just a nice and clean way to deal with iterating through a large volume of data, but also, and this is kind of almost giving you an answer for some of the other problems you have to solve later. But using those generators, you're able to, especially for the image data generator, you're able to kind of add some transformations to the images, right, to perform data augmentation. So this is for the images, but then we will concatenate it with the numerical features, right? We have 2 methods that do this, and just iterate through it with a while loop. Oops. And then you might want to weight the data, how important each data is, by the number of alerts per class, which is particularly useful in the case where you have, so here is just a binary classifier, but let's say you're training multiple binary classifiers and there's a big imbalance in your data set. You have more of one class than another. It's nice to be able to kind of weight the importance that you give to each class. And even here, I believe that Nabil had more data that is not a BTS transient than data that is a BTS transient. So that's one way to weight it. And so you might want to weight it either by alerts, by object. You can weight it by different things. And yeah, so logically, the fewer examples you have, the larger weight you're going to give it to ensure that the model isn't just going to try to only learn from the larger sample to get a decent score, which is a problem that you can have. And those are the 2 kind of mechanisms that we have. So we have some early stopping. based on the validation loss. And we have also a reduced learning rate on plateau, meaning that if your loss starts to plateau, so it's like your model isn't really learning anything anymore, you have this that's going to reduce the learning rate to try to reach to get closer to the local minima that you're close to, and just get a better accuracy out of your model. And then we have the more general early stopping that just, if for too long, even if we reduce the learning rate, nothing's happening, this is going to allow you to just stop your model from running, which is good because you don't want to, overfit the data. And this is honestly the simplest and best way to do it. And this is where weights and biases come in. So with weights and biases, what we're able to do is to initialize a project. And then within that project, every time you run your training loop on your model, you have callbacks that are going to send that data to weights and biases, like the loss and the accuracy, or even more stuff. It's just up to you, whatever you want to look at. And then there you have some amount of visualization where you can see the influence of each of those parameters on the results. But also that's you can use weights and biases for versioning, so you can track the different versions of your models without having to locally save everything every time you run something. And that also allows you to not have to really worry about adding a bunch of code just for plotting stuff. Weights and biases takes care of that for you. We're using an Atom optimizer, right? So it's just very popular. It just works well for a ton of science cases. And one thing that I want to mention, I commented here, but for all of those that are using a MacBook, you might want to replace whatever import we had above for the optimizer with this, or even just here. Use the legacy one simply because the new one is not working well on the new Silicon Mac, so the M1, M2, and now M3. And seriously consider doing it because the performance gains are something like ×4. So it's important to not forget about it. And yeah, so then you go through training the model. So this is not even necessarily using weights and biases. You can, right? But you don't have to do it. It's just to train it locally once to just see if with the data set that you have and whatever you have in place right now, without data augmentation is already enough for the model to learn. Is, as you can see, the loss clearly goes down while the accuracy goes up, even though it's pretty high at first already. So the goal would be to kind of come up with metrics, and this will be your first task, right? So this is just a very basic way to calculate the validation accuracy. Just run it on your validation data. But there's way many more metrics that you might want to look at, right? So like a ROC curve or an AUC, an F1 score, precision, recall, all of this kind of good stuff. And either you can implement it yourself, or honestly, sklearn has a ton of tools already to do it. So if you want to just learn how to use those, it's completely fine. And ideally plot the results, right? You could run some of those metrics for the different epochs, or just even for the latest one. So this will be your first set of tasks, is to go through the notebook, right? So being able to actually set up your environment if there's some challenges here along the way. I don't think you should have, but if you do, that's the first thing to focus on, of course. But then the idea would be to run your model for several epochs locally and kind of come up with metrics to evaluate it. And then to go further, we are going to use the weights and biases sweeps. So the grid search that I mentioned during my my presentation, to kind of play with the different hyperparameters that are just, it's too much of a grid to kind of play with by yourself locally. And so when you come up with this, the best way is to have, compared to, I mean, this is a notebook, right? So we have just code here and there. But if you want to be able to run it with weights and biases, one requirement is to come up with a proper training method that goes through the entire training loop. And that just sends everything to the logger from weights and biases. And the config that it gets is the config that is configured for the sweeps of weights and biases. So I'll go through this quick because this is exactly the code that you've seen above. And then you have a method that just says, okay, so sweep training, how does it work? You initialize weights and biases with a config if you want to pass a config for it. And then you can just call your training loop. But what we'll do is that instead of passing a config that we define here, to also be able to keep track of whatever values we used for the grid search and being able to go back to it once we train our models, will so what you can do is go to your weights and biases account that you just created. And there's a sweep feature in the navbar on the left side. And there you can create a new sweep. And when you do, they're going to ask you for a sweep config. There's already a base config that is given by the sweeps, but some stuff is missing. So what you just want to do is go to this notebook, double click the cell, just get whatever is here and copy and paste it in the config on the weights and biases webpage. So when that's done, you can just confirm the creation of your sweep, and they're going to give you a URL, which at the end has the sweep ID, which is what you need to pass to your notebook. So the whole, like the way weights and biases works is that it's not that your model is going to run on their servers or anything. It's just logging whatever you're running on your own infrastructure. So it's just a logging tool. And so, yeah, you need that ID, that unique identifier to be able to send the data there. And what's going to happen is that it's going to run as many grid searches as you want, right? And for each of them, your model is going to run locally for how many epochs it needs with the early stopping. And then what I'll do is that weights and biases is going to get all of the data from that training loop, process it with some process of decision making, come up with, okay, so this value might be worth changing, not this one. And it's going to send it back to your notebook with a new configuration to use for the next training loop. And this is, you're going to repeat that process n times, depending on whatever number you pass here. And at the end of it, when your sweep is done, you can have some nice visualization of all your different metrics, including a parallel plot, which is, I can show it, I guess, in the presentation. Just this nice plot where you're able to see on all of the different hyperparameters that you passed in the config, what value each of the training loop use. So each of the training loop has one color, and what's the validation loss, or you can change that metric. You can also check directly the accuracy if that's what you're more interested in. And you can see very easily visualize what were the best parameters that gave you the best model. And what you can consider doing is to then run another sweep, but constraining further on your different metrics to kind of get more precise values for whatever good model you had and try to improve it further. And also you can have some tabular format stuff where you can see the importance of each of the features on the loss or accuracy that you got. Yeah, so that will be your second and last task will be, so to create your own sweep and weights and biases, right? Run this notebook with the basic sweep that you have here. And then ideally the idea would be, because this, as you've seen on the one training loop that we run earlier here, I mean, the accuracy is not bad, but it's not great. You want to run this in production. The data set itself is more limited than what we would have in production because this is only publicly accessible data. But I tried it myself with data augmentation, with fine-tuning, running a bunch of sweeps. You can have very nice accuracy, something like above, I think, 0.85. I think I had something like this, right? Just with some basic changes of adding some data augmentation. So the idea would be to create a sweep, maybe increase the worker count to kind of explore the parameter space a bit better, and try different loss functions or optimizers, maybe change the way the weights are initialized, perform data augmentations on the cutouts, not the numerical features, and play with the model's architecture as well. This is definitely something that you might want to do because you could have very different results depending on the architecture that you're using. And you can definitely use some of the commonly known architecture like ResNet, EfficientNet, or even a more basic CNN that you just come up with yourself. And you can also play with what numerical features you pass to the model. So either you can pass the raw features, or kind of as I mentioned, you could also compute some features out of the ones that you have available from the many alerts, or let's say the alert history for an object. So all of the alerts before the one that you're running inference or training on, you can definitely compute some extra values there, which might help the model learn a little quicker. And yeah, improve the so the 0.6, when I say improve the time needed for inference, this is not essential, but the reason why I put it here, this is not much of a task for you guys, but it's rather just something in general to keep in mind, is that regardless how good your model is, if you have an architecture that is super intricate and that makes it so slow that you cannot run it in real time, there's no point in doing so, except if you want to run it on let's say the data releases that I mentioned, right, where you get something twice a month, then that makes sense to have some long running stuff. But here, the goal being to run in real time and to help the scanners, you want to have something that can run reasonably quickly, which of course depends on not just the architecture of your model, but just the architecture of your machine here. But you have to imagine that if something is just unreasonably slow, both to train and to run inference on, it's not worth it. You'd rather have something that maybe has a little less of an accuracy, but is usable in real time. And yeah, I mean, be creative, just especially for those of you that might have a more developed interest for machine learning. Whatever you learned before, just try to apply it here, and just have fun with whatever dumb and crazy ways you can kind of change the models and the hyperparameters and whatever strategy you can use to stop the learning process at the right time.
So I think we can thank Theo, and then we can ask some questions. Okay, I think Theo. Yeah. All right, we have some. Looks like we already have a question on Zoom.
Yeah, so let's start with Sarah. Or maybe not. No, maybe it wasn't the question. Then Shaban. Yeah.
Yeah. Hi. Yeah. Thank you. So in one of your slides, you mentioned about the 5 models and 5 classes, right? Can you show that slide again?
Yes. Let me share my screen again.
Thank you.
It would be this one. Yeah.
Yes. So these like 5 classes, it's related to the 5 independent classifiers, right? Because you have 5 independent classifiers, so that you can classify them up to 5 classes.
Yes.
Am I?
So, yeah, that's exactly it. So it's basically just 5 different models, 5 different binary classifiers, each just classifying one of the 5 classes.
Okay. So if, for example, if we have like more than 5 independent classifiers, so we'll have like more than 5 classes then, right?
Yeah, and so that's kind of the idea of having different binary classifiers rather than just one neural network that has, not binary, but a set of classes, is that if you have newer data as the survey just progresses and people just, simply just label more stuff, discover more stuff, you're able to just train one dedicated model without having to integrate it and change your existing model that has multiple classes in one, which means maybe when you're going to retrain those, you're going to have not as good performances as you did. So that's the kind of incentive of why it's better to just have binary models rather than just one that has multiple classes.
Okay. Okay. Yeah. Thank you. I have another question now. So in the notebook, you mentioned about the accuracy. So in those things, so do you also plot the ROC curves that you mentioned? Like
yes. So we don't. So in the notebook itself, no, it's not plotted.
Real time, like when you do this real time analysis. So in that you do this ROC and AUC curve plotting, because I think that is more like visualized thing to do the graphical analysis easy, I think.
So if your question is, do we do it on like the real-time stuff that we run it on? Was that a question?
Yes. Yes, yes.
Yeah, so I don't believe we do. I think this is used in benchmarking the model and training it. But when we run the model in real time, there's no, I mean, Nabil that is training the model might actually look at some samples of nightly alerts and rerun it on and kind of have a look to understand, what might be something that he could improve on, and then he might plot those curves. But in general, at least for the scanners, this is not something that they will even bother with. They'll just look at the score, look at whatever alert they get, try to kind of understand for themselves, okay, so what's the threshold that I should put on that score that I'm interested in?
Okay, I see. Yeah.
And yeah, I mean, a good example is I received an email from Nabil yesterday telling me that, so he used the features that are here, right? And for instance, one thing he doesn't use is the real bogus score. And you could imagine that the model would learn from it.
Yes.
The real bogus score that is also from another machine learning model, right? So you might imagine that this thing will learn from it, but apparently he had some performance issues where it would just give a high bright transient score even for those with a low real bogus score, meaning that it's bogus. And so that's one thing that is nice about having those binary classifiers and those metrics to evaluate your model, is that it's easier to figure out what in the data that you fed to your model is missing or is just not used as you expected to, and retrain your model and get your something decent quicker than if you had just a multi-class model.
Oh, okay. Yeah. Okay. Thank you. Thank you very much. And thank you for the wonderful talk. Yeah.
Thanks.
Adam, do you want to speak up and ask your question?
Yeah, so how do we handle some rare transients like Killenaway? So what happens in the machine learning system when we kind of identify a new rare transient like Killenaway?
Wait, you mean like, does it identify bright transients like Killenaway?
So let's say we don't have so much data on some kind of rare transients, and so what are the approaches in ML so that we have taken to identify some rare transients like Killenaway?
I guess so. I mean, the goal of the data here isn't really to directly tell you if it's a Killenaway. It's rather phenomenological or stuff like this. It's just, is this alert bright enough, or does it look like, with the different data that you have, does it look like it's going to get bright enough? But then characterizing what it is, I guess that it's a different process that the scanners go through, and this will have to involve kind of time series stuff where you look at the entire light curve.
And so just for a plug, so tomorrow we'll be talking about, so Brian's going to be talking about light curve classification, source classification, and then we'll have a dedicated anomaly detection talk on Friday. So some of this stuff is coming up over the next few days. So yeah, it's coming. Anything else for Theo? All right, well, thanks, Theo. That was really great. Yeah, so in terms of, so I suggest that, so we'll get into groups, work from now until lunchtime. And otherwise, it'll be kind of the usual schedule. We'll kind of disappear for lunchtime and then come back around, those around will come back around too, and so on. So thanks, everyone. So we'll leave Zoom open and all this stuff.
Yeah, I'll stay around today. I have a meeting at some point for like an hour or so, but I'll be around. So I'll stay on the Zoom, and if you have questions with the notebook, you can just send it in the chat or or ask Michael to.
Yeah, we'll make sure to get Theo on the, did we add you to the Slack, the dedicated summer school Slack yet, Theo?
think I am there. Yeah.
Okay, all right, okay. So you can tag Theo that way too. All right.
What time do we start the Zoom meeting again?
So we'll keep it open for the next 30 minutes because I think lunch is at 12:30 today, and then we'll start again at an hour and a half in 2 hours from now at 2 Central.
All right, thank you.